Good morning, welcome to new lecture. Today I will explain the relation between derivative of moment and shear and derivative of shear force with respect to the section location, and moreover I will solve several examples. I will draw moment diagram, shear diagram, so we will practice, and you need to practice this topic a lot because it is very important topic. And in future, you will need that for civil engineering major and mechanical engineering. This is very important topic. You should learn and you should be able to apply, because in future, in order to understand, for example, in civil engineering major, concrete design, steel design, or for mechanical engineering, machine design course, you will need all this. So please practice and learn the concept, and anytime if you have question, please feel free to send email. As soon we have simply supported beam subjected to distributed load, and this distributed load can be uniform or non-uniform. Here assume it is non-uniform and it is a function of x. So the length of the beam, it is L. This is simply supported beam. I assume one element of this beam, and the length for this segment, it is very small. I show with differential length dx, and this distributed load, it is function of x. If I draw free body diagram for this segment, small element, I have beam, internal forces, here shear force, axial force, bending moment. The length for this element, it is dx. Another side, because of this variation in the length, or here the section distance from point A, for example, it is x, and here it is x plus dx. So internal force will vary small amount. For example, here axial force will be m plus dn, shear force v plus dv, and bending moment will be m plus dm. We have external load, and external load, it is function of x, and it is wx. Let's look at the equilibrium of this segment. So this is free body diagram for that is small differential length dx with all internal forces and external load. This piece should be in equilibrium. So if I write summation of forces in vertical direction equal to 0, I can write v minus v plus dv minus w times dx is equal to 0. V upward positive minus v plus dv downward, for that reason it is negative, minus wx times dx, it will be resultant force for this small element, is equal to 0. From here v and v, they will cancel each other, so minus dv will be equal to w dx. From here I can write dv over dx is equal to negative wx. This means derivative of shear respect to the x, it is equal to distributed load intensity. If I take moment respect to cut point of O, for example this point, what I can write? I can write m plus dm, m plus dm minus m minus v times dx plus W times dx. This will be resultant force. Resultant force location up to point O, it will be dx over 2. This will be moment force times distance moment. W dx times dx over 2. Let's see what else. I'm taking moment respect here to point O, m plus dm minus m minus v times dx plus w times dx over 2 is equal to 0. From here, m and m, they will cancel each other. Dx times w times dx over 2, this will be equal to w dx squared over 2. Pay attention, dx is very small length, differential length. Dx squared will be much smaller because a small quantity squared will be much smaller. For example, 0.1. 0.1 is small number. 0.1 squared, it will be 0.01. So it will get much smaller. Because this term is very small, so you can neglect the effect of this term and assume this goes to 0. From here I can write dm minus v dx is equal to 0. I can write dm over dx is equal to v. This means differential of moment respect to x is equal to v. Differential of bending moment respect to x, it is equal to shear force. If I take one more derivative of this, second derivative of m respect to x will be equal to derivative of v respect to x, that will be equal to minus wx, means second derivative of moment respect to x is equal to derivative of shear respect to x, that is equal to intensity of the load. So from here 1, 2, 3. These result, it is very important, you should remember this. Derivative of shear respect to x is equal to a distributed load intensity. Derivative of moment respect to x, it will be equal to shear force. And second derivative of m respect to x is equal to derivative of shear respect to x, that is equal to intensity of the load. Let's now look at several examples. Simple problem. Cantilever beam means one end is fixed support, another end is free. Beam A, B, the length for this beam is equal to L. It is similar to the balcony in one building. It is cantilever structure balcony. Is subjected to, for example, concentrated load here P. I want to show internal force diagrams. Shear force, bending moment. Shear force, bending moment. First step, I should find reactions. AY here, if I assume upward, I can find it. Summation of forces in vertical direction is equal to 0. So AY minus P is equal to 0. From here, AY will be equal to P. If I take moment respect to point A, reaction here MA will be equal to PL. Now, if I cut this beam in the X distance and I show free body diagram, this is a segment of the beam, this is X, free body diagram, external load P, internal forces in positive direction V, M, N. And we don't care because we don't want to draw the axial force diagram, and it is equal to 0 because we don't have any forces in axial direction or any inclined load. If we have inclined load, that load will produce force in the horizontal direction or axial direction. But here N is equal to, or Nx is equal to 0 because these are function of x. It is good I show as a function of x. Vx will be equal to summation of force in vertical direction. Vx minus p is equal to 0. Vx will be equal to the p. If I take moment respect to cut point O, I can write minus mx minus p times x is equal to 0. From here, mx will be equal to negative p times x. Now, x is equal to 0 means point B. What is the shear? It is P. X is equal to L. It means point A. What is the shear force? P. So, shear force always it is constant number and it is P. X is equal to 0 means point B. What is the M? Moment. 0 times number, it is 0. So, it is 0. X is equal to L means point A. Moment will be negative PL. Negative PL. And it increase linearly PL because this function describes one inclined line. So this is linear. This is shear force diagram, bending moment diagram using classical way free body diagram. Without of this you can draw it much faster. How? Let's assume we don't have free body diagram. First step, I will find reactions. Then for beam, always I will start from left and I will move to the right. At left, reaction P up. So I will move up P. There is no force. I will continue. At point B, P down. I will move down P. I will close diagram. This is shear force diagram. Bending moment. Bending moment. At point B, it is free end. Free end. What is the moment? Moment, it means force times distance. Tendency of rotation. Moment produce tendency to rotation. At point B, we have force, but there is no distance between point B and B. So P exactly, it is at point B. Point B, distance from point B, it is equal to 0. So always at free end, always, free end, always, moment is equal to 0. If I apply concentrated moment at free end, it will be equal to concentrated moment. But if I don't apply anything, free end moment always is equal to 0. So at point B, moment is 0. If I move from right to left, just before support, if I cut it, what is the moment? Moment, it means P times L. The magnitude, it is PL. Negative or positive? First of all, this is internal moment direction. So if I write equilibrium equation, I will find negative. But even if I visualize deformation, this beam will deform like this. If you have balcony or cantilever beam, apply force here, it will bend like this. Underneath of the beam, the length will decrease. So it is subjected to compression. Underneath of the beam, compression means negative internal moment. So it should be negative. There is no force between. So the variation of moment should be linear. So with one inclined line, you will attack 0 to negative PL. It will be moment diagram. Let's now look at to the next example. Next example, it is again cantilever beam subjected to distributed load. So point A, point B, the length for this beam it is L, the intensity of load it is W, uniform distributed load. I want to draw moment diagram, shear diagram. Shear, moment. First step, I will find reactions. Reaction in the AX is 0, we know this is 0, because summation of forces in horizontal direction is equal to 0, so AX will be 0. AY, summation of forces in vertical direction, AY minus W times L is equal to 0. So AY will be W times L. AY upward positive minus W times L, it is resultant force downward, so negative. AY minus W times L is equal to 0. From there, AY will be W times L. If I want to find moment reaction here, M at point A, I can take moment respect to point A, so MA counterclockwise positive minus this load, it wants to rotate this beam respect to point A clockwise, so negative W times L, this is force, times L over 2 times the distance of resultant force up to here, L over 2 is equal to 0. From here, MA will be equal to W L squared over 2. So moment will be equal to W, let's I write here, MA reaction moment will be equal to W L squared divided by 2. Now I can follow classical method, cut at X distance from point B, show free body diagram, W, internal forces, V, X, MX, NX. NX is 0, Vx, summation of forces in vertical direction, equal to 0, so Vx minus W times X is equal to 0. Vx will be equal to W times X. If I take moment respect to cut point O, so what is the moment? Moment Mx minus, because it is clockwise, minus W times X over 2. It wants to rotate this piece, this segment, respect to point O clockwise, so it is negative, is equal to 0. From here, Mx will be equal to negative W x squared over 2. This is line equation, this is parabolic second order curve shape. So at x is equal to 0, if you plug here, means point B, shear is 0. At x is equal to L, shear force, it is WL. So if you attach, this will be shear force diagram, one triangle. This is Wx and this is 0. From this equation, if I want to draw a moment diagram, moment diagram at x is equal to 0, moment will be 0. At x is equal to L means point A. Instead of x plug L, it will be negative WL square over 2. Because it is parabolic shapes, curve, you will draw one curve, you will attach 0 to the W. L squared over 2. Derivative of moment, it is shear. Derivative of second order equation, parabolic shape, it will be inclined line. Derivative of inclined line, it is distributed load intensity. Derivative of inclined line will be one horizontal line. So that is right. But once I want to draw curve and attach point A to the B using one curve shape, second order, this blue one is right or red one is right. Both of them it is curve shape. Both of them is curve shape. You see the blue one, the red one. Which one is right? Which one is right? Think about that. Derivative of one function means the slope of that function. Derivative of bending, it is shear. Means the slope of moment diagram, it is shear force. Here from left to right, from left side to right side, shear force is decreasing. So the slope of this curve from left to right should decrease. In the blue, you see the slope from point A to point B continuously is decreasing. So the blue one is right. If I choose the red one from point A to point B continuously, slope is increasing. So this is wrong one. So the blue one is right answer. Pay attention to this, it is very important. And the slope of one curve, for example, we have this curve, we want to measure the slope. Slope means you will draw horizontal line and one tangent line to the curve. You will measure this angle. This means slope of one curve. You see in this kind of curve or in this kind of curve, here is slope bigger, here is slope goes to 0. So, here from left to right, because shear force is decreasing, the slope of this curve is shear force, because derivative of bending moment it is shear. So the slope should decrease, and in this blue one, slope is decreasing. Okay. Homework problem for the next session. For the next session, please draw moment diagram and shear force diagram for this simply supported beam subjected to non-uniform distributed load, and the shape is one triangle. Intensity here it is W pound per feet and the length is L. For the next session, draw shear force diagram, bending moment diagram for this beam. Beam, simply supported beam, is subjected to non-uniform distributed load and the shape is triangle, and the intensity here it is W pound per feet and the length it is L feet. Next one, simply supported beam subjected to non-uniform distributed load. Again the shape is triangle but symmetrical one. This is L, the maximum intensity. At mid-span it is W. and from here to here it is L over 2. So for this beam, subjected to triangle load and non-uniform, you see, and it is not symmetrical. Here, triangle, but it is symmetrical. For both of these simply supported beam, please draw shear force diagram, bending moment diagram, and this is your homework problem. Next session I will draw and I will explain, you will double check your solution. Thank you so much for watching this lecture. See you next session. Bye bye.